Fusion and fission are cousins, the yin and yang of nuclear physics. Both turn matter into energy using the most famous equation in all of science, E = mc squared. The equation tells us that matter can turn into energy, and when it does, it gets multiplied by the speed of light squared, a very big number. Both fusion and fission convert a little bit of matter into a lot of energy, so how do they differ? Fission means to come apart. Imagine a tablet of Alka-Seltzer dissolving in a glass of water. Fusion happens when atoms come together, when two become one. In both cases, we end up with a little less mass than what we started with. That missing mass multiplies by c squared to become E. In fission, the fizzing happens on its own. Radioactive elements such as uranium and plutonium split apart without any prodding from us. This makes fission relatively easy to control. It's why it's used in all existing nuclear power plants. Unfortunately, the stuff that uranium and plutonium fizzes into is toxic and radioactive, creating the byproduct that we call nuclear waste. Fusion is cleaner and more powerful, but it's much more difficult to achieve. It requires slamming hydrogen ions together with such incredible violence that they overcome the repulsive forces pushing them apart. As a result, they fuse into helium. Today, fusion only happens in places with incredible temperatures and pressures, like the center of the sun or a hydrogen bomb. But scientists are trying to squeeze hydrogen atoms together with powerful magnetic fields or laser beams, allowing us to control the fusion reaction and extract its energy. Yet all this squeezing takes a lot of energy, much more than we've been able to get out of the process. Because of this, the first fusion power plants are decades, if not centuries away. Until then, fission has the only mc squared we'll be able to use for energy. For Scientific American's Instant Egghead, I'm Michael Moyer.